It's my pleasure to introduce the first speaker of today, George Boxer from ANS Lyon, who is going to give his first lecture about higher Coleman theory.
Okay, thank you very much for the invitation to speak here. I just wanted to say that I can't see the chat, so if you have any questions, just speak and I should be able to hear you. So the goal for today is to start filling out the sort of summary and explain some of the things from Vincent's overview talk yesterday. So first, I'm going to try to explain, I'm going to define these so-called overconvergent cohomologies. Sorry, finite slope overconvergent cohomologies with their sort of Hecke action. I'm going to explain that can be computed on small neighborhoods of these components of the ordinary locus. So these were and this sort of justifies the sense in which they're overconvergent cohomologies. We think of them as being on small neighborhoods of components of the ordinary locus. And to construct the spectral sequence, which relates them to global cohomology, and so this is the spectral sequence, which on the first page, you see a sum over these overconvergent cohomologies. And abutting to the cohomology of the whole Shimura variety. Okay, so and maybe just a sort of cartoon or picture to keep in mind of what we're doing here. So we have our Shimura variety, and then we have these components of the ordinary locus, which I'm just going to draw as points. So these are these different components of the ordinary locus. And sort of the first thing that we're going to do is sort of stratify our whole Shimura variety, maybe into kind of big strata. And just for some formal reason, there's going to be a spectral sequence that computes the cohomology of the whole Shimura variety, sort of in terms of the cohomologies with some support conditions of each of the strata. And then we want to explain that, in fact, each of the terms in the spectral sequence can also be kind of computed in terms of cohomologies with supports, just in tiny neighborhoods of these points. And somehow the key point in all of this is that we have these Hecke operators acting, and somehow the action of the Hecke operators is going to be telling us sort of how to choose the support conditions. So somehow at some of these fixed points, the Hecke operators might sort of be kind of contracting in all directions, but then at others, they'll be sort of contracting in some directions, but expanding in other directions, something like this. And somehow the action of the Hecke operator is going to tell us what kind of support conditions to take. So I kind of want to explain how that works now. So the first section of my talk is just going to be some generalities on cohomology with support. Can even begin with recalling the definition. So if we have a topological space and we have an open subset U and a closed subset Z, and maybe we have a sheaf of a billion groups, we have the functor of sections with support on the intersection of the closed and the open. So I'm going to write this in a slightly funny way, but I sort of like this point of view as we're going to see later. So this is the sort of sections on the open U such that the support of the section is contained in this closed. Okay, and then this is a left exact functor, and so we can derive it. This is the derived functor. And this is this cohomology with support. Okay, so let's list some basic properties of it. So the first thing is that it sits in an exact triangle with usual cohomology. So from the cohomology with support, you of course have a map just to the usual cohomology in U. And then you can go to the cohomology of the sort of complementary open by restriction. So U minus Z. And you get an exact triangle like this. And so in particular, this basically tells you that you can compute this cohomology with support in terms of just usual cohomologies. The next thing is that let's record some functorialities. Well, there's a functoriality in the open and a functoriality in the closed. So if we have two opens, U inside U prime, we get a restriction map from the cohomology with U prime to the cohomology with U. And then in the closed, if we have the inclusion of a smaller closed in a bigger closed, we get what we call co-restriction. And this now goes from, the cohomology with support in the small closed to the cohomology with support in the big closed. And what is this? Well, of course, it's just that if you have a section with support in Z, then of course you get a section with support in Z prime. Okay. What else do I want to recall? So we have what I call excision, maybe what topologists call excision. So it somehow says that really this cohomology only depends on the locally closed U intersects Z, despite the fact that that's not completely evident from the definition. So if U intersects Z is equal to U prime intersects Z prime for some other open and closed, so if they define the same locally closed, then these local cohomologies are the same. And so in particular, I guess I've been calling this both cohomology with support and local cohomology. I guess it sort of just depends what world you're living in, but these cohomologies are local in the sense that they only depend on the sheaf F in the neighborhood of this locally closed U prime intersects Z, U intersects Z. And then the last thing is that there's the spectral sequence of a filtration of a filtered space. So if we take a filtration by closeds, a finite filtration of X by closed, we get a spectral sequence, U1 PQ. And what we see is the cohomology with support in sort of ZP minus ZP plus 1 of X minus ZP plus 1. And this spectral sequence computes the cohomology of the whole sheaf on X. Okay, and so our spectral sequence in higher Coleman theory is exactly just going to be an instance of this spectral sequence of a filtered space. Okay, and now sort of as I was mentioning, the key thing in all of this is the interaction with the Heck operators. So I want to take a moment to discuss the action of correspondences on cohomology and cohomology with support. So the setup now, we'll have a correspondence, and maybe I'll call this correspondence T. So what is it? It's space X with two maps, which I'll call P1 and P2. And now, let's leave the world of general topological spaces, and let's say that P1 and P2 are finite flat maps of p-adic spaces or schemes, or formal schemes or something. And I'm going to assume that they're finite flat so that P1 and P2 are open on the underlying topological spaces, open and closed. And of course, there's going to be some slight problem in our setup when we're working with toroidal compactifications of Shimura varieties, but okay, this is only a problem at the boundary, and I'm just not going to talk about the boundary much at all. So let's not worry about that. And now we're going to have a sheaf, well, maybe say a vector bundle. And we need one more thing in order to define an action of this correspondence on its cohomology. We need a map between the two pullbacks. And now how are we supposed to let this correspondence act on cohomology? Well, the idea is that we sort of want to take the pullback by P2 and then take the trace by P1. And so what we're going to do is we're going to, starting with cohomology of this sheaf, we take the pullback by P2, as I just said, and that will get us onto the cohomology of the correspondence with values in the pullback by P2. And now we're going to use this map. So maybe I give this map a name and I also call it T. So I'm going to call everything T. And then we take the trace under P1 to get back down to X. And again, this trace sort of, we can define it because P1 is finite flat. Okay, so that's for the sort of cohomology without support. And now we want to understand, when do we get an action on cohomology with support? So, okay. So the point is, we're not always, I mean, you can't just take random support conditions and expect to get an action of the correspondence. There needs to be some compatibility. So, okay. So to explain this, the basic thing is that we always get a map, well, which goes from the cohomology with support in T of U intersect Z to the cohomology of U intersect T transpose of Z. So of course, maybe we would want to be studying just the cohomology with support in U intersect Z of U, but this is the thing that we sort of naturally get. And maybe I should explain the notation. So here, I mean, T of U means sort of applying the correspondence to, so you're supposed to think of the correspondence as being a sort of multi-valued function. You pull back by P1 and then you apply P2. So
George, I'm really sorry to interrupt. Can you try to write a little bit, like, if you could, I don't know, because like the T's are like gamma, the Z's are like 2's, the intersections are like lambdas. I mean, it's kind of difficult if we don't remember if you could, I don't know, maybe.
All right, I try. Yeah, I don't know. I'm not
your
very
pen
good
doesn't
at
allow this. I don't know. If you could, thanks. Yeah.
Okay, maybe I try to just write a little bit bigger and slower. Sorry. And then here, this is T transpose. So T transpose is you just take the correspondence and you apply it in the opposite direction. Okay, so maybe I don't spell out in detail the construction of this map, but just try to convince you that it's sort of the right thing. And you can look in our paper or in the talk I gave here the last time. I probably wasted altogether too much time on this. So the point is that if you just think about what happens when you take a section which is sort of defined somewhere and supported somewhere, and you try to pull it back, and take its trace. Well, if you want to end up with a section on the open U, it had better be that that section is sort of defined on the entire preimage under P1 of U. And thus, it had better be sort of defined on the set T of U. So we had better start in sort of T of U if we want to end up with a section. I mean, we should start with a section on T of U if we want to end up with a section on U. And then for the supports, it's sort of the opposite way around. You think that, okay, if my section over here starts supported on Z, then it's going to be supported inside P2 inverse of Z. And so its trace is going to be supported on sort of T transpose of Z, the image down here. Anyways, I hope I kind of convince you that you always get a map like this. And this is really the natural thing that you get when you try to study the action of a correspondence on cohomology with support. Okay, so what are we going to do with this? So maybe I'm going to go to a new page. So, oops. So first of all, if T of U is contained in U, and T transpose of Z is contained in Z, we will get an action on the thing that maybe we really wanted to study. So why is that? Well, I'm going to leave room for 2 more bullet points here and start drawing a big diagram. Well, it's going to start as a small diagram. So we have here this cohomology with support that we maybe wanted to study. And then we have this map T that we've just constructed. So going from T of U intersects Z, T of U. And now, by the 2 hypotheses we've made, we have also maps like this. This is just the co-restriction where we're enlarging the support, and this is the restriction where we're restricting the open. And so now, by just going around this diagram, we get a map from the space that maybe we really care about back to itself. And that's the construction. Okay. And now the next point. So in particular, this tells us how we would need to have arranged our open and our closed if we want to get an action of the correspondence at all. The next point is that if these inclusions are strict, by which I mean that sort of the closure of U, the closure of T of U is contained in U, and T transpose of Z is contained in the interior of Z, or something like that, then this sort of composition of co-restriction and restriction is compact. So I'm not going to explain why this is, but what I'll remind you is that there's a situation which is probably familiar, which is the case where there's no support. So if Z is the whole space X, then this co-restriction map is just disappearing because it's just the identity, and we're only considering this restriction map for a strict inclusion. And so that will give us a compact map. That restriction map will be compact. And so because sort of this is compact, that will tell us that this is also compact, or actually maybe its square is compact, but that's sort of good enough. And that will allow us to sort of take the finite slope part of this space. Okay, and now we can also go further if further we can keep iterating. So maybe u contains t of u, contains t squared of u, contains t cubed of u, and so on. And also z contains t transpose of z, contains t transpose square of z, and so on. Then we can build a big diagram So for example, here we're going to have the cohomology the cohomology of t of u intersect t transpose of z with coefficients in t of u, with coefficient in the open t of u with coefficients in f. And then we have also restriction maps and co-restriction. And we also have this thing with t squared u. We have another map t, so on, and so on. And maybe sort of the general element of this diagram is something like t to the mu intersect t transpose to the nz with coefficients in t to the mu. I mean, sorry, in the open t to the mu with coefficients in f. And now, why am I drawing this whole diagram? Well, on every single, so each has an endomorphism T. And all the maps become isomorphisms on the finite slope parts. So maybe to explain a little bit about this, the point is, I mean, this diagram is not really a commutative diagram because it has cycles, but it has the property that, I mean, if you start, if you take any two entries of it, there are sort of lots of ways to get from any one to any other place. And it has the commutativity property that somehow any two paths that you take, the resulting map only depends on the number of times you use an arrow labeled t. So for example, I mean, here we use t twice. And these maps are then in particular also factoring big powers of t on both the source and the target. So like, for example, why is the finite slope part of this the same as the finite slope part of this? Well, the point is that there's this map like this, and that map is factoring through this map, which is now this map twice, t squared. And so anyways, I like this laser pointer thing, but I'm not sure if that's very easy to follow. Anyways, so, right, and so why do we care about this? Well, the point is that we hope that as we go kind of down the diagram, these cohomologies are really kind of supported on smaller and smaller regions. And that's the sense in which we're proving some kind of analytic continuation results. So just to summarize this whole discussion, we have this kind of picture. So maybe here's our space X. And maybe here is this kind of fixed point. And I'll draw a picture of what my correspondence T looks like dynamically. So maybe it's sort of an attracting fixed point in this direction, but it's a kind of repelling fixed point in this other direction. And so in here, the dynamics kind of look like this. So the dynamics tell us how we should choose our support conditions, U and Z, for this to work. So basically what it tells us is that we should try to pick our sort of open set like this. So this will be our open set U, and we should try to pick our closed set like this in such a way that in this locally closed set, the sort of open boundary is in the direction that the dynamics are contracting, and the closed boundary is in the direction that the dynamics are repelling, okay? And that's kind of the basic game, because if we choose them like that, then, at least according to the way I've drawn the pictures, the set T of U is maybe something like this. The set T squared of U is maybe something like this. So they're sort of nested in each other. And similarly, T transpose T transpose of Z will be sort of this set maybe. And then if you apply it twice, you'll get maybe this set, and so on. And so these kind of places that we're analytically continuing to are maybe then tiny locally closed neighborhoods of the fixed point. So this little region here is something like T to the N U intersects T transpose to the N Z, okay? And so what we're kind of proving is that this local cohomology on this big locally closed set is the same as the finite slope part, at least, is the same as the local cohomology on this small set here, okay? And in particular, we had to kind of choose the kind of open and closed boundaries of our locally closed according to the dynamics of T. Okay, I hope that's at least roughly clear. Okay, so now we want to sort of apply this story to, well, the flag variety, which will then pull back to the Shimura variety. So let's talk about the flag variety now. Okay, so G is going to be the symplectic group with the sort of standard pairing. And then, as in Vincent's talk, we're going to pick the diagonal torus inside the standard upper triangular Borel, and then we have the Siegel parabolic, P mu, or maybe I'm just going to call it P for now, since we're not talking about the Shimura variety. And this is this sort of block upper triangular parabolic like this. And then we have its Levy factor M, or M mu, which is isomorphic to GLG times GM. Okay, and then we have the flag variety. And we're thinking about quotienting by the parabolic on the left, so that the group is now going to act on the right. And we have the Weil group. I recall for you the explicit description of the Weil group, although we're not really going to use it so much today. So I think tomorrow we'll interact with GSP4 enough that we'll need it. But so we can describe it as just thinking about how it acts on the basis vectors of our standard symplectic space. It permutes them, so we get a permutation of 2G elements, and it has to satisfy this. And inside that, we have the Weil group of the Levy. This is isomorphic to just a symmetric group on G elements. And then we have this important set, W upper M on the left, which is the set of minimal length of the cosets for WM.
Can I just ask, George?
Yeah.
I'm a bit puzzled because in the notes that Vincent posted on the website, he had a B and a P, and B was definitely not contained in P. So I'm a bit confused why the conventions have changed.
Well, there is P and there is P standard.
In the previous notes, B was definitely contained the block lower triangular stuff.
Well, okay, but yes, so maybe Vincent was also not taking B to be the upper triangular parabolic. But I am. Sorry if that's confusing. I mean, the point is it doesn't matter in some sense, but so we want B to be contained in P. And maybe for some reason, at some points, Vincent likes to not take B to be the upper triangular Borel. Yeah, maybe I should have looked more carefully at what Vincent wrote in the notes. Okay, well, so far it hasn't mattered, right? Okay. Right, and so I want to just describe for you this set in a few different ways. So, so sort of concretely, it's the same as this. I'm not sure how useful that is, but maybe a more helpful way to think about it is that it's the same as asking that W maps the dominant weights into the M dominant weights. So in other words, you can think about the dominant Weil chamber for the levy M, and this decomposes into Weil chambers for the group G, and that decomposition is indexed by this set WM. And what's basically the same is that this is the same as asking that the positive roots for M are contained in W of the positive roots for G. So, okay. And then, of course, immediately for us, we have the Bruhat decomposition, and this set also indexes the Bruhat decomposition. And I'm going to call this Bruhat cell CW. Okay. Right. And maybe we can also introduce the Schubert variety, which is the closure of CW, and that can also be written as a union of Schubert cells because it is an honest stratification. So maybe W prime, which are less than W in the Bruhat order of CW. And there's also this kind of open, which I'll call YW, which is just the union of sort of all the Bruhat cells which contain CW in its closure. So this is open in the flag variety. And of course, CW is the intersection of XW and YW. And you'll see how I'm going to use these in a moment. Okay.
Sorry, do you want CW, the union of CW prime?
Yeah, sorry. Sorry, in both of them, yes. Thank you very much. Okay. So now what are we trying to do? So we want a stratification of, well, the adic flag variety, or just the generic fiber of the flag variety viewed as an adic space, which is KP invariant, where KP is the Iwahori. And so I'm going to tell you what we're going to use in a sec, but maybe I'm going to give the example of P1 first, just to explain something. So let's take G equals 1. So basically what we want to use is the tubes of the Bruhat cells in the special fiber. So P1 of FP is sort of CW naught FP disjoint union C1 FP, this being, of course, just the point infinity, and this being the sort of A1. And so from these, we can take their tubes, maybe in the sense of classical rigid analytic geometry. And so these are opens in the adic generic fiber. And what are they? Well, this one is the sort of closed Tate disk around 0, and this is the open Tate disk around infinity, sort of both in rate of radius 1 in the obvious sense. And these two opens are the sort of standard example of a non-admissible cover. So they contain all the classical points, but they're not a cover of the whole adic space. So they don't cover P1 ad. There's a single rank 2 point missing. And now we can actually define not one stratification, but two stratifications by just adding this extra point to either one of these. So we get two decompositions. So the first one being that we take the closure of the tube over the Broughas cell. So we take the closure of the open Tate disk, and sorry, we take the closure of the closed Tate disk around 0 and the open Tate disk around infinity. And then the other thing is that you just reverse those. So you take the closure of the other one. Okay, so why am I even writing this? Well, it turns out that you can develop the theory with either of these choices, but it depends on which Heck operator you're planning to use. And the reason that I'm even talking about this is I want to answer David's question from yesterday about why 1 and W not switched between Vincent's toy model and Vincent's and the theory for the Shimura variety. So this decomposition is the one we're going to use, and this is sort of good for UP, and this is the one which would be sort of good for UP transpose. And the way to see that is that if you remember, we should be taking our open neighborhood to be an open neighborhood of the fixed point, which is getting contracted to, and a closed neighborhood of the thing which is getting expanded from. And as we'll see in a sec, UP is sort of contracting towards the fixed point corresponding to 1, and it's expanding at the fixed point corresponding to W naught, and vice versa for UP transpose. So that's kind of the answer, is that if you want to work with the UP operator, you're kind of forced to put overconvergent modular forms around the canonical ordinary locus and the sort of H1 with support around the anti-canonical locus, and then vice versa if you're working with UP transpose. But it doesn't matter because the Atkin-Lehner involution will ultimately identify these two theories. Okay. So now what's the stratification in general? So we find the stratification of the sort of adic flag variety by closeds. And what is it? Well, okay, I write the formula, but maybe it's, well, okay. So we take the tube over the union of the Schubert cells corresponding to elements of length at least R. Okay, and so I mean the confusing thing is, sorry, I don't want to scroll up all the way, but just like in the first of the two examples, sorry, no, it's right here. Sorry. So just like in this example here, we're doing the kind of funny thing that we're taking an open set, we're taking the tube over it, an open set in the special fiber, we're taking the tube over it, and then we're taking the closure of that. So somehow from an open in the special fiber, we're getting a closed set in the generic fiber, which, well, that's the price of wanting to work with UP rather than UP transpose in some sense. Anyways, it doesn't matter because we actually wind up doing both. Okay, so that's the definition of the stratification, and it's sort of evidently invariant for the Iwahori because the things in the special fiber are invariant for the Borel. Okay, and so now we get a spectral sequence.
What is that symbol between the U and the W? Is that a C? Is that a G? Is that
Sorry, that's, yeah.
No, not that one, not that one. It's in the middle. Sorry. It's in the very middle of that. It's a C.
Yeah, okay. C, yeah. Like that one.
Yeah, yeah. Mm-hmm. Okay.
Yeah, so we're taking. I mean, we're basically taking all the Schubert cells of dimension at least R, and we're taking the union of them, and that's some open in the flag variety, and we're taking the tube over that, and then we're taking the closure of that. Okay. Anyways, it's a definition, right? Yeah. And again, I should say, I mean, okay. If you don't like these tubes and closures, and you just want to think about the classical points of this thing are just, the closure doesn't change the classical points. It's just adding some higher ranked points, which you might not really want to think about anyways, but they're important to get a closed set. Okay, so we get a spectral sequence associated to this filtration, just the one that I wrote down before. So we're going to pull this stratification back to the Shimura variety. So we're going to take the cohomology of pi Hodge Tate KP inverse of ZP minus ZP plus 1 pi Hodge Tate of the flag variety minus ZP plus 1 of our automorphic vector bundle V kappa, and that's going to be converging to, doesn't make any sense. I should be taking cohomology. Converging to the cohomology of the whole Shimura variety. Okay, and now we want to analyze this a little bit. And so the first thing, maybe I'm not going to explain this too carefully, but well, okay. Let me write something. So this each term is breaking up into a sum over elements of the Weil group of length p. Of HP plus Q, well, of something else, and I'll explain why this is in a sec. But let me just write it first because that will already take a while. So we take the tube over XWFP intersected with the closure of the tube of YWFP. So that's the support of pi Hodge Tate inverse of just this open XWFP.
George, you use P both for the prime and for the index in the, yeah, that's quite confusing.
Well, yeah, okay. But Yeah, I'm sorry.
But in length W equals P, which of the P's you mean? You mean the prime P? Right?
No, that P is the index of the spectral sequence. Yeah, okay. I mean, there's the P, the prime, and then the P, the index of the spectral sequence. And yeah, maybe we shouldn't do that, but yeah. Okay. I mean, it wouldn't really make sense to talk about elements of a Weyl group of prime length, but yeah, okay. No, I mean, you're right. It's not
okay,
so
just
good.
to make clear, yeah.
Notation. Okay. So why is this? Well, probably I'm completely confusing you now, but basically this is because this locally closed ZP minus ZP plus 1 is itself a disjoint union of these sort of intersections. And so I write one more confusing thing, and then I try to explain some things. So if I didn't take this closure here, or for example, if I only think about these things at the level of classical points, this thing is the same classical points as just the tube over the Schubert variety, because after all, the Schubert variety is the intersection of these two things. Okay? So, well, that's now the definition, but we need to address why there's a heck.
George, have you considered turning your paper 90 degrees so that it's longer in the horizontal direction than the vertical direction?
I could do that, but I think that might cause a disaster if I do it right now. Like, I think to do that, I have to like change something. Yeah, I'm sorry, I should have done that. I think last time I did that and I didn't like it for some reason, but maybe this way is a lot worse because it's filling up a lot less of the screen. I mean, to me, it looks like it's filling up the screen, but not to you. Yeah, I'm sorry about that. I don't want to try to figure out how to do that right now. So, okay. So now the basic theorem is that, well, basically what Vincent already stated last time is that this HP plus, and I remind you what is HP plus in a sec. And the sort of Heck operators, T and T plus plus, act compactly. So I just remind you what this is. So recall that this monoid T plus, the set of elements in the torus such that the valuation of alpha of T is strictly bigger than or equal to 0 for all positive roots. And then inside that, we have the ideal T plus plus, and that's sort of the same thing with strictly bigger. Okay, and then this HP plus is just all the Heck operators associated to elements of T plus, or the span of them. Okay, so based on the discussion about actions on cohomologies with supports, so what we need is, so somehow we need T to contract the open and T transpose to contract the closed. So in other words, we need that the tube over the Schubert variety so, and now you're going to really get upset with me because I'm having in the same formula tubes and then parentheses for double coset operators, but okay, notation is terrible. So we need this to be contained inside the open again. And similarly, we need that we have the sort of opposite contracting property for the closed. But now for the transpose, which corresponds to taking T inverse. And moreover, these are strict when T is in T++. Okay? So that's the kind of dynamical statement that we need in order to get this action and have the correct capacity. Okay. So, well, anyways, ultimately, this is just boiling down to some linear algebra, although it's not necessarily easy linear algebra. So let me try to just roughly explain why this is true. So we need to understand the sort of dynamics of these Heck operators KPT, KP on, not P1, I'm about to do P1 on the flag variety on KP, but a sort of easier problem is to understand dynamics of just T plus on the flag variety. Well, so no correspondences, just the action of this monoid in the torus. Okay, so for example, and this is going to turn out to be a very easy problem. So for example, for P1, well, I guess you can even write it in coordinates, maybe. So if you have this matrix corresponding to UP, it's going to multiply X by P. And so what you see from this is that the fixed point corresponding to 1, which is sort of corresponding to the point 0, 1, is an attracting fixed point. And so that's why we wanted to take the sort of open around it. And this point BW naught, which is 1, 0, is a repelling fixed point. Or it's an attracting fixed point for T inverse, which is why we want to take the closed to be around it. Now in general, how do we kind of understand what the dynamics are like near the fixed points? So we need to write down some kind of coordinates. Coming from so let me explain what I mean by this. So for example, if you wanted to study the point corresponding to 1, that lies in the sort of affine space, which is sort of the opposite Brouhaus cell. So in other words, you take P times U bar, where U bar is now the kind of unipotent radical of the opposite parabolic to P. And you can do something similar for a general W just by translating it. Like that. And now this is good because it's very easy to understand how T acts on U bar. So U bar has a decomposition into root groups. So by phi upper M minus, I mean phi minus, the negative roots which are not in the levy, which is exactly the roots which are sort of occurring in this block down here of the corresponding root subgroup U alpha. And so conjugating W inverse U bar W is the product over alpha and W inverse of Vm minus of U alpha. And now we can split those into two groups, the ones which are positive and the ones which are negative. So down here, the ones just the same thing, but the ones which are not positive. Okay. And now what's the point is that according to the definition of T plus, here is on these roots. So T plus preserves these root spaces. T normalizes the root spaces. And according to its definition, when you conjugate from the right, it's sort of expanding. It's contracting these ones. And it's expanding these ones. Okay? And so this is telling us what kind of support conditions to take. And it's also allowing us to check that these support conditions coming from Schubert varieties are sort of the correct ones. So just to explain this, well, I want to introduce, using these coordinates, I want to introduce various neighborhoods. So these are these things that in the paper we call CWFP MN. This is for M and N rational numbers. Well, we're just going to take some balls in these root spaces to define some neighborhoods. So we'll take the product of I just want to make sure I get the notation the same as it is in the paper. So I'm going to actually look at my notes. Okay, so we use M. Where, okay, these, I mean, this is somehow the closed Tate disk in the root space of radius p to the minus n, and this is the sort of open Tate disk in the root space of radius p to the minus n. There's a reason we make this choice, which has to, well, anyways, I actually will probably explain in a sec. And then we also, so this is an open space in the flag variety, and we also want to introduce a sort of partial closure of it. Which we do not like this. And sorry, but I probably want the other one. And so now I take the closure. So this is now sort of neither a closed or an open, but it's a locally closed subset of the flag variety. And to relate this back to the things that we've seen before, so for example, CWFP00 is just the tube over the Schubert cell, and CWFP 00 bar is this locally closed that we are taking the cohomology of before. So it's the intersection of XW XWFP intersect FP bar, and then these, when you take M and N big, these are sort of the tiny locally closed that you can take the cohomology of when you analytically continue. And anyways, so I guess I just wanted to explain that you just write down these neighborhoods where you put the sort of closed directions of the locally closed in the direction that the action of the Heck operators are expanding, and you put the open directions in the directions that they're contracting, which is what we were sort of expecting to do before. Anyways, okay, so I probably shouldn't say any more about this. I think it's kind of confusing, but
you have U alphas with a little circle, ones with a bar and ones with no decoration at all. Which ones are closed, which ones are open, and which are the rest?
Right. So yeah, I'm really sorry. I think this is a problem with the classical language more than with the subject. But so, I mean, up here, both of these are classical rigid analytic spaces, and they're both open, but this is a closed Tate disk and this is an open Tate disk.
Okay, right.
And then here we're taking the closure to get something closed, which is not a classical rigid analytic space. We're taking the closure of a closed Tate disk. Anyways.
Okay, thanks.
I was, yeah. Okay.
I left out a symbol in the subscript. Like, I'm not sure how many of them there are. There's an intersection with a phi minus that's missing and under the partial closure with the otherwise your product.
Yeah, sorry, you're right, sorry. Yeah, sorry, I've just been writing the same thing over and over again. So like it's always W inverse phi m minus intersect phi minus and phi plus. We just, I mean, we took, I mean, I was writing the same thing over and over again, but let me just remind you how we got here. I mean, we took this conjugated lower unipotent radical and then broke it up according to which things are now positive and which things are negative. That's all we did. Okay. Any questions?
Well, first of all, thank you very much for the talk. Let me give you a clap. And yeah, so let's go for talks and for questions.
I have a question. Is the Hochstate map here an affine map?
Well, yeah, so I'll talk about this a little bit next time. I mean, it doesn't really make sense because we don't put in any kind of geometric structure. So, I mean, we consider, let me just remind you, so we're considering pi Hodge Tate KP from the Shimura variety at finite level to the flag variety mod KP. And so this we're just viewing as a topological space with the quotient topology.
Okay.
So it doesn't really make sense to talk about it being affine. But on the other hand, I mean, of course, you have sitting over at the flag variety and the perfectoid Shimura variety. And so, I mean, what will be true is that if you sort of take, an aphanoid here,
okay,
which is sort of invariant by KP, then its preimage over here will be aphanoid.
Okay.
Something like this. And for that, we're going to use basically the theorem that this map is affine in some precise sense. Yeah.
But I mean, to obtain the spectral sequence, do you push your computation, I mean, your shifts from the Shimura variety to the flag variety and do the computation there, or?
No. We just pull everything back. Yeah. So I don't want to consider any sheaves or any cohomologies on this space. At least I don't. I mean, one probably could try to do it that way, but that's not what we do. So we pull everything back to the Shimura variety. So at the end of the day, you should imagine that we're really just using the Hodge-Tate period map as like a ruler to define some random regions that we're going to take the cohomology of. But it turns out that it's incredibly powerful for understanding how the Heck operators push them around. That's basically what I've been trying to explain. And yes, Siegel, you're right. Not for the toroidal compactification, for the minimal compactification. So yeah, when we prove the vanishing theorem next time, I'll say something about this. Thank you.
Thank you.
Well, I have a question. It's a kind of a follow-up of a question I asked last time. So when you consider this hot state map, I mean, obviously you decompose the flag variety with respect to the Bruja decomposition of the special fiber, right? So because it's a very difficult problem to write double cosets for deeper Iwahori subgroups like mod p square or mod p cube. It's a difficult combinatorial thing. Well, you're not doing this anyway, right? I mean, you're doing.
But we're only. I mean, okay, so we're only using t plus. So I think with respect to your question, let me just say that we're only working at Iwahori level out of some convenience. So as long as so this whole story works for any KP which has an Iwahori decomposition.
But so, it's I mean, like it's not indexed by, it's not a Bruja decomposition if you go deeper. It's not on the special fiber. It's just something like it's like working mod p square or mod p cube.
No. But we're okay. I see what you're saying, but we're not going to try to look at. I mean, we're going to ask maybe ask that KP is contained in the Iwahori and it has the Iwahori decomposition, and then we'll just use the same stratification.
No, but if the KP is smaller, then you don't have a map like this.
We don't have a map like what?
Well, at perfect width level, you have some GQP equivariant map. Then if you want to quotient by some random KP small enough, then you'll have on the right-hand side also, you cannot quotient by something bigger on the, you still.
No, I mean, this diagram, sorry, this is the eraser. This diagram right here is for any KP, for any open compact.
Oh, but you're saying on the right-hand side, you'll use only like the stratification with respect to the Iwahori, even if KP is smaller?
Yeah, if you want to think about it like that, yeah. I mean, but just to keep in mind, I mean, it's not really the stratification with respect to the Iwahori, right? I mean, you should think that we're considering the Bruja stratification of like the CP points of the flag variety, or just the points as an adic space, whereas the Iwahori has something to do with like the QP points.
So if KP is smaller, you have a finer stratification, but you'll only use the coarser one. You'll put together.
No, we use exactly the same stratification. If KP is one, I mean, KP, no, I mean, let me just say this. I mean, the strata that we're considering are not KP orbits. KP is a profinite group. And so its orbits on the flag variety are some like kind of profinite sets that you don't want to think about too hard. Like they might look like, for example, you know, they could look like ZP or something, but the points of the flag variety are like looking like CP, or or you could think about the points as an adic space. So, I mean, the stratification is, I mean, these Bruja cells are not orbits for KP. Maybe I can say something, but I mean, I know what you're thinking about. What you're thinking about is the fact that we have this kind of decomposition of the QP points of the flag variety into orbits.
No, I was thinking more about the FP points.
Well, it's the same. I mean, this is just the pre-image of the FP points, but I mean, there's some decomposition like something like this, right? Where the decomposition is literally indexed by orbits of the Iwahori. And then you're right, if you replace the Iwahori by some deeper group, it's very hard to understand
exactly
this decomposition. But we're not thinking about that decomposition. We're thinking about the decomposition which is somehow maybe of like the CP points or just the adic space points. Right? I mean, this is only about the QP points. I'm not sure if what I'm saying is clear. Like if I looked at the CP point, if I put CP here instead, but still considers the Iwahori, there would just be an enormous number of orbits. Because you also have all the non-QP rational points. And each of the Iwahori orbits are like some kind of profinite set sitting inside the flag variety.
Okay, I'll have to think more. Okay.
No more questions from. Well, it looks like we are done. So let's thank George again.